Good morning, everybody. It is my pleasure to introduce today Dr. Osvaldo Diegues. Osvaldo has obtained his PhD from the University of Santiago, Spain, and after that he moved on for his postdoctoral research, and he worked in Cambridge University, Rutgers University, and MIT. And since 2008, he has been working as a scientist at the Barcelona Materials Science Institute, which is one of the Spanish national labs. Osvaldo's field of study is application and development of atomistic simulations to materials in general, and more specifically to ferroelectrics and multiferroids. And in fact, this will be the topic of his presentation today. So, Osvaldo, the podium is yours.
Okay, thank you very much, Ilan. Thank you, Noam. Thank you to the rest of the research committee for inviting me to visit again Israel for the first time for your purposes. So, I'm going to talk today about my field of research, and that is atomistic simulations of materials. I'll try to show mainly examples of how to use these methods, when to use these methods, and what are they for. As I said, my name is Osvaldo. I work in the Institute of Material Science in Barcelona, and I've been visiting Rutgers for the last few months. So this is what I'm going to say. First, a few words about generalities of the field, and then examples of my past work in multifunctional oxides, mainly ferroelectric films, multiferroic materials, a bit on domain walls to give a sense of other things more complicated than usual that we can do. A very brief mention of a couple of more examples that have nothing to do with this, to show how these methods are of general applicability. A little bit about how do they work, how do we develop them, and if I have time, a bit about future plans. So I'll start with the atomistic simulation of materials. And in my field, at least, this is a very often quoted paragraph from the Feynman lectures of physics that illustrate very well what is the building block of all this. Feynman asks what would be the sentence with the most scientific knowledge in the fewest words, and the answer for him is that everything is made of atoms. So this is the basic assumption in the kind of simulations I do. Everything is made of atoms, and atoms can be as simple, you can model them with something as simple as a hard sphere. Then once you decide how your atom looks like, you need to apply a well-established physics theory that will give you how this atom will interact with other atoms to form a material. And you can go for the simplest case, that is Newtonian mechanics. So for hard spheres, you can assume just that the spheres are free, they only interact when they collide, and when they collide you conserve kinetic energy and momentum, and you can track the positions and the velocities of these particles for as long as you want, if you have a computer. And this is the third ingredient in what I do. To solve any kind of equations, number of equations like the ones that appear here for any kind of interest system, and to analyze the result, we are going to need computers like this IBM from the 60s or early 60s. And with this, you can get complex behavior. Actually, I chose this model because it's one of the very first atomistic simulations that were done by Alder and Weinrich. And even with such a simple thing, you can begin to get the feeling of materials. They found that there is a first-order transition, and here you can see an image from their simulations in which a liquid phase coexists with a solid phase. This is in 2D, in 3D is the same thing. Today things have evolved, not in the basics, but in the details. We don't do hard spheres usually anymore. We use atoms that have nuclei and electrons. We use the best theory we can for this kind of system, which is quantum mechanics, and in this case, most of the time-independent Schrödinger equation. We still have to use computers, and I'll try to show that you can predict or understand the properties of many materials properties. So this is an image to show that first there are many methods you can use, all of them based on atomistic simulations. You can go with classic systems, no quantum mechanics here, and treat your atoms as particles that interact through a force that you have an expression for. It can be like a van der Waals force, whatever kind of force expression is relevant for your system. And the simplest thing is pair potentials. You can go with force fields or shell models. You can acknowledge that there is something quantum mechanical in your atoms, and put electrons in some simple way here, and you go with tie binding methods or embedded atom methods, but you still need to fit your expressions for your interaction between atoms to some quantities that come from macroscopic data, so from solids or molecules or whatever. And then there is another whole field that is called, in physics at least, first principles simulations. The chemists don't call first principles this big dot here, but in our field we usually do. And these ones, you don't require, in principle, you don't require any macroscopic information to fit. You just assume that no matter the material you have, it's a collection of nuclei and electrons. They follow quantum mechanics. You don't need to know what is the lattice constant of silicon to treat a silicon nanotube, any silicon material. So, well, I just wanted to make the point. These are the thousands of papers that were published in the last 5 years. The point of this is that what seems to have the best compromise between accuracy that goes from less accurate to more accurate, and a system size you can deal with that goes from smaller systems like small molecules to a whole virus that you can study with pair potentials. A good compromise is DFT. So I'll talk very little about DFT, but most of the results I'm going to show are computed with density functional theory. So what are people doing with this and other things? Well, this is, yes, I thought a good way to show what the field is up to. Hi, is this is what they call a word map. So the bigger the font size, the more hits there are in the text from where I created this. These are the most common words in a text made by 700 emails from a European list on atomistic simulations, where you get basically job ads and meetings ads. So DFT is still by far the most used method, although people are going more and more towards many body methods like GW or quantum Monte Carlo that was around here. About applications, there is a lot going on in energy, oxides also, surface as interfaces. There is things going on in energy, but I mean, this is just to give an idea of what kind of systems and what kind of thing we do. So I'm going to show in a bit of detail this example on simulations, and it's about ferroelectric materials. So the ferroelectrics I've studied are all perovskites. Okay, this is a perovskite structure. For those of you that are not used to it, there are many materials that crystallize in this form. There is a what is called the formula. The chemical formula is AbO3. This is the B ion. Those are the cation. These are the A cations, and the B ion is surrounded by oxygens, 6 oxygens. So this is an oxygen octahedra, and most of the electronic properties come from the binding between the B cation and the oxygens. This is a perfectly cubic perovskite that exists only for a few of them. Most of the time, what you have is a distortion of this crystal structure. So either the cations move along some direction, like this one that moved along the z-axis if you want, or the octahedra distort, like this case, or they rotate. When the the atoms, the cations move along one of the directions, the symmetry of the charge is not, the material is not center symmetric anymore. You have a symmetry in the charge, and you have a polarization. This is an electronic polarization. This is the equivalent of a dipole moment, if you want, in a molecule, but for a solid. Okay? So in this case, that atom went up and created a polarization in that direction. By symmetry, you can have exactly the same thing, but it can go down. So these are polar materials, those that show some that are non-center symmetric. To be a ferroelectric, a polar material has to be switchable. So you have, if you apply a field in the down in this direction, you have an hysteresis loop, and you go to the other phase. Okay, so you can switch the polarization between the two, and this has technological applications. For example, in memories, this is the PlayStation 2 that includes ferroelectric memories. Because you have two directions of the polarization, you can encode ones in one of the direction and zeros in the other direction, and this will stay. So this is memory that doesn't change when you unplug your computer, and is used. It has a segment in the market. All ferroelectrics are piezoelectrics, so they can use in ultrasound imaging. A piezoelectric is a material that when you squeeze it, it gives you a difference in voltage, because, as I said, they are not center symmetric. So in ultrasound, well, you use it both to emit the ultrasound and to analyze the image. The same effect is used when you need to control very little movements of a mechanical device. You can also do this by using the piezoelectric effect. You can move very little a mechanical device with a voltage. An example is an AFM tip, and they are always used in capacitors because they have a very good ratio between the dielectric constant and the breakdown field. So the study I'm showing here is not for bulk ferroelectrics, but for ferroelectric films. And what is particular of them is that when you grow this, what I say here is epitaxial films. These are coherent epitaxial films. When you grow them, the properties of them change, because they are on a substrate and they have to adapt to it. By choosing which substrate you have, you can choose what properties you have. And in this case, to show how this changes, for example, if it was bulk, barium titanate goes to zero polarization. The Curie temperature, the one of zero polarization, is around here, 140, 130 Celsius. If you grow it in the right film, you can have polarization, for example, to match larger temperatures. The other point I want to make about ferroelectric films is that they can, in the lab, they can really be created coherently on top of substrates to a very good degree of perfection. So what affects, or one of the variables that affects the behavior of the film is going to be this strain. There can be more. There can be the interfacial properties changing, but one that for sure you are going to have is this strain. So we wanted to isolate the strain effect from the rest of the effects and study it with our methods. So again, to make the point, if you have a substrate and you are going to grow barium titanate on top of it, barium titanate will have some lattice parameter. But because you grow it layer by layer with molecular beam epitaxy or some kind of chemical vapor deposition, when it grows here, the unit cell is going to have to adapt to there. Okay, and you do it layer by layer, and the next layer adapts, and the next layer adapts, and in the end, you end up with some strain here. And you can grow them in the lab for hundreds of nanometers, even coherently. So this, what gives you, as I said, is a handle on what you want to do with your film. You just pick the substrate you want, and then your film will be more or less compressed. Let's see what happens when they are more or less compressed. And this is a work that I did in the group of Vanderbilt, of David Vanderbilt and Karen Rabe, and we used density functional theory to do this. So how do we do this? So we can map how different the phases that you can have can be, and you can compute the energy for these phases and see which one is the ground state, which phase is the one that the system wants to take. You do this for any misfit strain that you want, so for any distortion of the film that you want. And here they are labeled as they used to label before our study in the literature. It doesn't really matter exactly what each label is. What it matters is that each label corresponds to a different direction of the polarization. So we want to see in this case what is the effect on the polarization change. I mean, how does the polarization change with the strain? So when there is a lot of minus is compressive strain, when you squeeze this, the central atom goes up and you have a polarization in this direction. You can simulate this for different degrees of strain, and there is a point in which there is a phase transition. This curve that corresponds to this phase is not anymore the most stable one, but there is what we call here the R phase that takes over, and then there is the AA phase. So what happens is that as you squeeze the material, the polarization rotates. This is the R phase, and this is the AA phase. And this is a second order phase transition in the sense that it's a continuous movement of the polarization as a function of a strain. And this had not been reported before. So this is what you get at 0 temperature. Okay? Those calculations at DFT are usually, or by default, done at 0 temperature. Depending on what material you are studying and what properties you want to study, this might be okay or not. If you are working properties at room temperature of a material that anyway only will change phase at 800 Celsius, probably the effects that you get with temperature are small and you still can go towards this route. But if you want to study a transition that occurs at a low temperature, with temperature you need to do something else. And to take into account temperature, in principle, you go to statistical mechanics and you have to do averages, weighted averages of energies of possible configurations. With DFT, this is going to be impossible because the system is too large. The fluctuations you can have can be on different length scales, so the system is large, and on top of it, you need to do many of these calculations. So there is no way to do it purely with DFT. An approach you can take is an effective Hamiltonian or effective potential, in which you go to your material, you pick which variables are important, and then you come up with an energy as a function of these variables. And this is what they did, for example, in the group of Vanderbilt 95. The energy is expanded as a function of the local strains, so for every cell, how much it contracts or it expands, and the soft mode vector. So what is the soft mode vector? It's a concept that is very useful in seeing transitions in ferroelectrics. So like barium titanate. This, you can see the transition that I show from the cubic. So the cubic phase is the one at high temperature, and the polar one is the one that occurs below 130 Celsius, as I said. So you can see that there is a mode, there is a phonon in this structure, in the perfectly cubic one, that becomes soft as you lower the temperature. So as the cubic is stable in high temperature, but there is a transition, and the mode condenses. So the atoms go through the motions given by the mode. So in this case, the mode is something like this. It's going up and down, vibrating there. If you lower the temperature enough, it will, the structure will go down. So this is the energy of the cube, of the perfect cubic structure. And below some temperature, if you displace the atoms according to that mode, you lower the energy. Okay? And you can compute the polarization and map the energy versus the polarization. Now, how good is this says that there is a minimum here. Okay? And this should correspond to the polar structure for the theory to be perfect. It doesn't correspond exactly, but it's very, very close. So if you look at what happens to the material in the polar structure, the displacements are very, very similar to the ones that the atoms want to do there. So you get a point here, and obviously you get the other configuration, so you get that other minima. Because these materials are so close, I mean, these reproduce so close the real minima, you can use these displacements as your variable. So instead of using groups of 5 atoms with their electrons and everything, you just use a component in that displacement. So for every cell, you allow it to move a little bit. Then you build your energy that has, well, you do it sensitive, with some sense to take into account these main variables. And with this, you can evaluate the energy many times in a cheap way. So you do this, in this case, with a so-called Monte Carlo method. I'm not going to give details. The point is that you can compute a phase diagram at a finite temperature. And then, well, again, you see different phases, but you can see that it's possible to do calculations based on DFT and finite temperatures. If you look at experiments, it's not easy to measure exactly where the polarization points to. It's easy to measure if there is a polarization or not, but where it points to is difficult. It seems that for what I know about barium titanate, this is quite accurate, other than the diagram is shifted, which has to do with shortcomings of DFT. But it's a tool to study these materials. This illustrates another thing you can do with DFT. Once you have this theory, with DFT and the effective potentials. Well, once you have the theory, you can begin to vary more things in your system. So in this case, what I do is at 0 temperature, but different load strains of stresses on the film. So it's not that you are going to have a device where you are pressing there. We don't do it because to know what happens in this case. We do it because this kind of handles give you a broader perspective. So in this case, what we find is that there are 8 perovskites here that in principle, they show very different properties when you grow them as a film. This corresponds to the 0 stress. But if you use this kind of approach and you look from further, what you can see is that the phase diagrams are very similar. What you find then in real life is that the stress corresponds to different positions. So this material looks very different from this material because it has 2 different phases, but it's because it's just another part of the phase diagram. It's also good when the experimental results agree with whatever you predict. So this is an example in which after this group measured these films and agreed with our results. So that's for ferroelectric films. Now, most of my research in the last 3 years has been in multiferroics. Multiferroics combine ferroelectrics and materials with magnetic ordering. So as I said before, you can have ferroelectric RAMs, memories, where you use the electric field to change the polarization, and with this have 1s and 0s. This is not what usually happens. Most of the disks that used to be in computers, what you do is use a magnetic field to switch a magnetization. You can ask yourself, what if we had something in which we combine both things, and you could use the electric field to switch the magnetization or the magnetic field to switch the polarization. And this can be useful because there are problems with both types that maybe are absent with a multiferroic. So a multiferroic is just a material that is ferroelectric and ferromagnetic, although now people call multiferroic also to some antiferromagnets. So there's a lot of interest in multiferroic materials, and a lot of research has been done, starting with this paper in which they found that in films you get a polarization for this material that is larger than any of the typical polarizations in perovskites, like 3 times more than in barium titanate, and that they had some kind of magnetic moment. So why bismuth ferrite? And half the papers that are about multiferroics are about bismuth ferrite or how to improve on bismuth ferrite, or more than half. So why bismuth ferrite? Because there are very few multiferroics, and even less that are multiferroic at room temperature, right? Which is the temperature you want for your device. As I said, it has one of the largest polarizations known. It's quite easy to grow as a film or as a bulk. It has a very simple structure which helps theoretical studies, and it still shows new effects like very large photovoltaic currents or domain walls that show conductivity. What is not so good about bismuth ferrite is that the coupling between the magnetic and the electric properties is small. So you want to change the polarization with the magnetic field, but it turns out the magnetic properties and the electric properties, there is not a high degree of correlation between them. And also it has a very low ferromagnetic moment. So how can you improve on this? Well, one approach is to look at what is bismuth ferrite and try to improve what you have. So again, this is a perovskite structure with big cation, with the irons there and oxygens between them. So you have octahedra surrounding them. Now, it's a bit more complicated. The distortion that occurs for this one is a bit more complicated than the one for barium titanate. Well, obviously you have the bismuth there, and what happens is that the cations displace along 1-1-1 direction, and the oxygen octahedra rotate in antiphase. Okay, here I remove some of the octahedra, so it's easier to see. So you get this displacement and that polarization. This is a rhombohedral lattice, as I said, with a high polarization. The temperature at which this becomes nonpolar is 800 Celsius, and the Néel temperature for antiferromagnetism is around 370. Now, question that we can address. Are other metastable phases about bismuth ferrite that maybe have better properties if we can make them stable? And this is ideally suited for the kind of methods we use. And we do this by coming up with guesses, trial guesses, that you you heat a little bit so they get disorder, the atoms begin to move, and then you let them cool down and see where they want to go. So most of the trials will end up in the ground state, which is what I said before. But for the case of bismuth ferrite, and this is again not usual for perovskites, there is a huge lot of minima that appear, of the order of tens. So there are many different phases that it can take. One is this one that is nonpolar, and where the octahedral rotation follow a different pattern. So this comes from our simulations. Does it exist in the real material? It does exist when you go to high pressures. So this is the phase that the material takes experimentally at around somewhere between 5 and 10 gigapascals. What else is there? There are these so-called super tetragonal phases, because they are technically they are not tetragonal, but they have a very large ratio between this length and this one, the C/A ratio. So in perovskite it is around 1, and in this kind of thing is around 1.3. Barium titanate is around 1.0304. So can you stabilize these phases that appear for the solid, but is there a way to stabilize them? And yes, there is. And similar phases to this appear in ferroelectric fields, if you, again, draw them under strain. So we can, apart from looking at experiments and where they show up, we can find how well we agree with experiments by computing at different strains what happens with the films. We find that they are stable at around 5% of strain, as the experiments show. We can check where the pressure phase transition occurs. We find it's around 3 gigapascals, and again, this is close to the experimental result. Now, why does bismuth ferrite have so many metastable phases? The reason has to do with the lone pair of bismuth that we can see here. So bismuth 3+ has 2 electrons, 2 s electrons, that don't bind in many of these configurations. In some do, but in many they don't bind to oxygens, and the system has to accommodate them. And basically, almost any direction in which the system accommodates the lone pair will give you a local minima. So there are many phases you can study, and this is the first study kind of that mapped consistently these phases that appear. I'm going to talk a bit, maybe fast, about the domain walls, just to show more complicated things you can study with DFT. The origin of this study is a paper in which they show that, well, ferroelectrics always show domain walls, right? If the ferroelectric was perfectly infinite, then all the atoms would want to move along the displacements patterns that I said, and that would be the ground state. But in real materials, you have a surface, and this would give rise to charges in the surface, and this would cost energy, so the system breaks into domains. And in the case of bismuth ferrite, they have a very unique, at the time, particularity that is that although bismuth ferrite is an insulator, a clear insulator, with a band gap of 2 to 3 electron volts, the domain walls are conducting. So you measure at the middle of the domain, you find no conductivity. You measure at the domain walls, there is electric conductivity. So why? One hypothesis that people put forward was that at the domain wall, the atoms rearrange. Because they rearrange, the electron levels also change, and maybe the band gap closes, so the electron levels get closer to each other, and there is conductivity. This we can check with density functional theory to see how much these structural properties changed and what happened to the electron levels. For this, you have to model domain walls. So you will have a domain wall, and to one of the sides there will be your bulk, and to the other side there will be maybe your bulk, and if they are exactly the same, the solid material, then you have just the whole solid. There is no domain wall there. I represent this with arrows for the polarization and with curved arrows for the octahedral rotation. You can have something very similar, which is polarization pointing in the same direction, but the octahedra go in the opposite way. And this I represent like this. And here you don't really have a ferroelectric domain wall, but you have a ferrodistortive domain wall, if you want. The octahedra don't match, so there will be some strain there. And finally, the same way you pick your polarization to go in the 1-1-1 direction, you can pick any of the equivalent ones that goes to any of the other vertices of the cube. So like this one. Okay. So you have to see how many combinations you get, and you have to find the energy of them and try to learn from the pattern that you find. If you bother to do them all for the 1-0-0 direction of the domain wall or for the 1-1-0, you end up with a set of them. You can compute the energies to form any of these domain walls, and then you can see what patterns arise here. And one interesting thing is already that contrary to ferroelectrics where there is no octahedral rotation, the ones that keep the ferroelectric polarization in the same direction are very high in energy if the octahedral rotation don't match. So what is costing energy is not the polarization change, which is what happens in most ferroelectrics, but the octahedral rotation. You can see it here that if you have, this is the real cell we used for the simulations. It has 120 atoms. There are one domain that is replicated. There are two domains that are equivalent, and what we see is in the middle of the domain, you get the ground state. This is the bulk. This is how the solid wants to behave. And in the domain wall, you get the phase at high pressure. So what you get here is that the octahedral network is very little distorted because it can accommodate a mix of two phases. Another thing, if you are familiar with domain walls in magnetic materials, is that in ferroelectrics they are very, very sharp. So it's like 2 unit cells. This is what happens with pure ferroelectric materials. The same is true here. There is very little octahedral distortion, and you can go on quantifying this argument, although I'm going to very briefly just say that it's all reduced to a matter of how unhappy the octahedra are, basically.
This is zero temperature?
This is zero temperature, yes.
So the difference in energy is very small.
The difference in energy is not that small.
So fluctuations would not actually make any...
This is our assumption. Because precisely bismuth ferrite is very stable until up to 800 degrees. So, and for example, we can look also at the what is called the density of states. So how many states for the electrons are there for different values of the energy of these states. Up to a point, that is the Fermi level, you will fill those levels, and then you have your conduction band, and if there is a gap in between, you will have an insulator, because the electrons will not be able to move from here to there. What we see is that there is no change in this. So this goes against the interpretation that there is a rearrangement in the domain walls, and goes in favor of another interpretation of experiments that were done later, and that show that there are oxygen vacancies, and oxygen vacancies donate electron levels, and there you get your conduction. I did other materials that are, mostly in the last years I did ferroelectric and multiferroics. I worked with other materials, although given the time constraints I'm going to go very fast. A fuel cell is a cell where you get, well, for those of you that don't know, you get hydrogen atoms, hydrogen molecules going to an anode, and oxygen going to the cathode. The hydrogens, in this particular kind, the hydrogens split here, the proton go through this membrane, the electrons go to electron current, and here they recombine, and you get water molecules when the protons and the oxygens get together, and you get, as a result, electricity here, water, and heat. The problem with this is that this recombination, this oxygen reduction reaction, is very slow. So you need a catalyst. The most used catalyst is platinum or platinum-based materials, but it's very expensive. Can you use something else? There was a group at the time, an experimental group, collaborating with the group I was in MIT, and they wanted to study rhodium sulfide materials that are, well, but by now they are commercializing. At the time, basically nothing was known about this material, so we did a very preliminary exploration of its main properties. I'm not going to talk about them. You can compute, again, energies, structures, and in this case, for example, you see that the compounds are in the convex hull of this diagram, so you expect them to be stable, and in fact it seems that the three of them appear in the nanoparticles they use. At the very beginning of, the first project that got me interested in DFT things had to do with metal nanoparticles. They have applications in medicine. Well, like this one is an application in which they use gold clusters surrounded by what is called lipoproteins, which is what cells want to eat. So cells, cancer cells want to eat. So they arrive here, they want to eat their food, and they end up stuck with a gold nanoparticle. When enough gold nanoparticles attach to the cell dies of hunger. And apparently, according to this has been very effective. You can use them in combination with polymers to look at what they call self-healing materials. So you make a scratch in a material, you raise the temperature a bit, and the material heals. A typical use of nanoparticles is as catalysts because of their surface properties. Just this other one, very cute, is these are a solution of iron containing nanoparticles that they use in water that is poisoned with arsenic. The arsenic wants to bind to the nanoparticles that contain iron, and then you use a magnet and you remove them. And apparently again, this is working very well. We did some simulations that I'm not going to go in detail. My only point for this transparency is to show how much the field has changed. In 2001, during my PhD, I did this, and achieving 17 particles in a nanoparticle was a new development. The previous studies stopped like at 7. Nowadays, even for iron nanoparticles, probably you can do hundreds of atoms in the nanoparticle, and this is only 12 years. Now, okay, I'll talk a bit about the methods we use, or contributions I have done to the methodology development, just very briefly. So, one of the methodology developments I've done, all these calculations are done with software that is, it's very, it has been built by groups of people along the years. It has more than typically 100,000 lines of code, and they are quite complicated, but they are very robust nowadays, and you can use them to simulate all these materials. In particular, there is one developed in Spain that is Siesta, because of this acronym. It uses the same approximations and many other DFT codes. The nuclei are treated as classical particles. The electron interactions are treated with density functional theory. That is a way to just reformulate the Schrödinger equation to make it treatable computationally, or more treatable. The interactions between these electrons and the ions are done with what is called pseudopotentials. You have to use a basis set to expand your Schrödinger-like equation, and in Siesta, contrary to many other codes that have plane waves, in Siesta you get localized orbitals. You need boundary conditions, and in Siesta you the ones you had were periodic boundary conditions. So when whatever atom goes, if an atom goes through a side of the cell, it will come from the other one. And the thing that is particular to Siesta is that is linear scaling. What this means is that for conventional first principles codes, if you double the number of atoms in your cell, you have to use between 4 and 8 times more computational time. They scale with the square to the cube of the number of atoms. Siesta is designed in such a way that this scaling is linear, so it allows you to go to larger sizes. The main implementation that I did in Siesta had to do with a problem that appeared, that it doesn't appear in the quantum chemistry codes usually when you are studying molecules, but it appears in the solid state community, which is if you have a molecule like this one and you are using periodic boundary conditions and the molecule turns out to be polar like water, then you are having some spurious interaction between your molecule and the images. And you can try to correct this in several ways, and one that we used is this alternative way, which is a multigrid solver, in which you find an approximation for the potential in the sides of the box where your molecule is, and then you use what is called a multigrid algorithm, which is basically you use grids of different sizes to relax the equations, the discretized equations that you wanted to solve for this. This has advantages, which is, for example, that is linear scaling in the spirit of Siesta. It allows you to do treatments of your molecules or your clusters when they are in a solution of water and ions by solving what is called the Poisson-Boltzmann equation. And for this particular setting, the person that developed this multigrid way to deal with differential equations is actually Brandt and Weissman. Here you can see the comparison between the previous method, that it was a FFT method, and the new one. You get convergence. This is the box you need to enclose the molecule in, And with FFTs, if you want to achieve the convergent result, you need to have a very large box, and this will cost you computational time. The bigger the box, the more hours of computation you need. But if you use a multigrid, you can do it much faster with much smaller boxes. And the other application I wanted to mention is calculations at constant polarization. This is a tool that we did to further, to help our study of ferroelectric. So before, if you remember, I told you that there is a cubic phase at high temperature for barium titanate that at low temperature goes to tetragonal phases, either up or down. And I told you that these tetragonal phases, the displacements of the atoms, are very similar to the one of the soft mode here, but not identical. So one question that arises is, can you get a double potential that goes exactly through there? So can you find, for a given polarization, what is the energy of the most stable configuration? And well, why would you do that? Well, for one reason, because it will help you to search for metastable states that might otherwise, if the surface is complicated, they might be hidden. You can compute properties of the material that are related to the derivatives of the energy versus the polarization, like the electric constant, which is basically this curvature. So if you have the curve, you can get the electric constant. And if you are building effective potentials or effective Hamiltonians, you can use the polarization as a variable, and then you have a map of the energy versus the polarization, so you can fit this expansion. We used it to study different kind of materials. This is an example of a ferroelectric that is potassium nitrate that mixes not only cation movements up and down, but octahedral, in this case, trimer rotations. We found the exact method is ours. This is an approximation that existed before. And we found, for example, a mapping that is already different from the usual double well potential that I showed before, because it has a peak here. This has some implications. I'm not going to go into detail. Since the chairman is up at my 45 minutes.
I suggest that, yeah, I think we would like to hear about your future.
Okay. So I showed this map before, and two of the research directions I want to go with is what they call high throughput methods and also larger scale methods. So larger scales. This is an example I took from the group I was in Cambridge, although I had left already. What they did is they were interested in studying the propagation of cracks in silicon. So this is a problem that has a size for your simulation that is huge, because the crack will move along nanometers and nanometers of silicon. So you cannot, you cannot even imagine doing it with only DFT. So what they use is what is called a QMMM method, in which you treat the quantum mechanical part with DFT, and you treat the rest of your material with something that is cheaper, like those potentials I told you about. So in this case, the crack is moving. You are doing the simulation quantum mechanically where the tip is, and every time the crack opens, you move the area in which you do the simulation, and you have to kind of get together these two parts, but there are ways to do it. So you are basically getting DFT accuracy for a system that otherwise you couldn't treat. This, for applications of the research I want to do, it's very easy to imagine then, again, in the context of ferroelectrics or multiferroics, although this can be applied, as you saw, to any kind of material. In the case of multiferroics and ferroelectrics, there are questions that you want to answer about the domain walls, for example, that you are not going to be able to answer with only DFT, because the number of atoms you need, again, is very large. So you can, for example, you can try to find out what is the real reason those domain walls conduct, or how do the properties of the material, the dielectric constant, or whatever you are interested in measuring for your material changes with the presence of the domain walls. Why are in many materials the domain walls are rough? For any of these things, you need to have many atoms in the simulation cell, like for many simulations with real materials that you work with, and this is a way to go. And there are plans to implement it, for example, in Siesta. Well, this was more structure that you get into these films and that you cannot get with DFT. That is one of the possible directions. Another one that many people are working, not many, but that groups are beginning to work in the context of atomistic simulations is high throughput methods. What this is to try to use computational resources to come up with new materials. And the way to do it, there are different levels. It's still at the very beginning, and there are different levels of sophistication. I chose an example here by the group of Gerb Seder at MIT, in which they have a method to guess with some good, and all these things we would have to define, but they guess which materials can be novel, or what kind of structures you can get that nobody has found experimentally yet, but they might be the ground state of some combination of materials. And these dots of different colors represent 1, 2, 3, or 4 new structures that they found for ternary oxides. So the way it works, again, I envisioned this initially for something in the context of ferroelectric and multiferroic materials. The way it works, you could, in our case, you could use strain again as one of the variables, but the other variable to find new ferroelectrics and new multiferroics with improved properties, or in general any material, is to substitute ions. And this is very commonly done in perovskite. So many times you get solid solutions, like in bismuth ferrite, you can have bismuth cobaltite and a solution of the two. So a way to go in this direction would be, again, to devise similar tools that, like the ones I just showed, but to combine, to come with reasonable approximations of which substitutions you do in the perovskite and what improvement do you get. And again, this can be a perovskite or can be something else. And this you go towards in the route of finding new multiferroics with better properties that, in the case of bismuth ferrite, don't appear. And just almost to finalize, those are just two things to give some context to my research and my future research, but in a more general view, I work kind of with applications in mind, I work in methodology development, but most of my papers or most of my scientific output is in the field of applications. The ideal combination is when you need to treat some material, but the methodology, or not all of the methodology, is there. So you get to develop the methodology and and use it for new materials, and that nobody has been able to tackle problems nobody has been able to tackle so far. Being this a new department in material science, it could be a very good opportunity for me to interact with members of this department and Tel Aviv University and apply the experience I have with these methods to other kind of materials that are of interest here. So just to finalize, I hope to have convinced you that first principles methods are useful together with experiments to get understanding about the properties of materials. You can use them to find new materials that don't exist but can then be tested in the lab following the guidelines of computational discovery, and also they can be used to build more coarse models with information from first principles, but that can be used for larger scales. About my research, I try to show that it's problem driven, that I've done applications to different kind of materials, and that I have developed methodology that's needed, And with this, thank you again for listening to me.
Thank you. I'm sure there are some questions.
In your calculations of the ferroelectric thin films, so in a real world thin film, you also mentioned there's a surface, and the electrostatics plays a major role there also. So how do you take into account possible, screening of interfaces?
Okay, yes, that's true, and in many ferroelectrics that's the case. The films I showed were films like barium titanate, where there is no charge in the layers are neutral, and also I didn't say it, but thanks to your question, these are simulated as short circuit boundary conditions. So you assume that you have a metal.
The question about the temperature, can you explain a little more how do you do the calculation at final temperature and how do you see
Yes.
different
So
conditions?
no, no, no directly. We use a stochastic average by using a Monte Carlo. So we use a Metropolis algorithm that will explore the configurations of energy. We accept configurations of energy that are low enough to be representative, and then we'll do averages on these configurations of energy. So what you see is what is the pattern that appears there. So you could go and compute free energies then, but it's not the way we do it.
Can you put that slide back?
Yes, I think this.
Hamiltonian.
Yeah, the computer just froze, so. I'll have to force quit and open it again.
So where is what you were just told, where is it folded now in here?
Where is it?
The temperature effect.
So again, this is the energy for any configuration. So you pick the soft mode components and you pick the local strains, and this is the energy that this will give you. The energy that as the temperature rises, the system is not in the ground state. So the minimum of this energy is the ground state. At zero temperature, what would the atoms do? As the temperature rises, there are other states of energy that are available, and those are the ones that I'm sampling with the Monte Carlo method. So,
You sampled the Boltzmann distribution.
yes,
This
yes,
is your Hamiltonian.
yeah.
So the temperature enters in the sampling.
if you have energy for all the configurations?
With Monte Carlo.
Yes.
Yeah.
So
More questions, please?
When you showed this cases where you quenched very quickly the system and it formed a different structure, and then you mentioned that this structure can be accessed at higher pressures in the experiments, and then you calculated the transition pressure, and it was actually a little bit lower.
it was lower than in experiment. Yes.
And my question is, why is it lower? And
So-
the reason I'm asking is because I suspect that in the experiments, these transitions may occur through defects which do not exist. So if it was a perfect lattice in the experiment, it would even be higher. So why does the DFT miss so much?
So, well, one thing is there is for sure there is a role of what is called the exchange correlation potential, because if you change this approximation, then you get, for example, if you go to LDA, you get a better agreement with the experiment. You get a.
This was GG?
This was, yes, one of the GGAs. So LDA gives you a transition pressure of around double, but the LDA gives you worse transition for the misfit strain films. So we went in the end with the best compromise. Also, experimentally, it's not that clear where the transition is, because they see phases. As you raise the pressure, it seems that up to 3 or 4 gigapascals, you get the ground state. Then you get an area where they don't really know what they have.
Yes, but also underestimation of the band gaps, right?
With LDA,
Yeah.
you underestimate the band gaps, yes. So,
But he's looking at the ground state of
Yes.
simulation, so
yeah,
they should be quite
as long as you are not measuring
very different.
optical properties or something that depends crucially on the band gap, the structures are very good.
Question from an experimentalist. Is there any hope for the multiferroids in applications, or is it a little bit...
There has been like 3,000 papers published in the last 5 years on, let's say 10 years, on bismuth ferrite and multiferroids. There are experimentally some concepts of device that work, in the sense that there are people that have made the system switch its magnetization with an electric field and this kind of thing. But there has been so far no easy fantastic discovery on multiferroids, and yes, they will be perfect for whatever, memories or something like this. So there is work, a lot of work going into it. It's not clear that where the devices will come from and what they will serve for. There, again, Cesar.
I guess that your work on the domain boundaries will crucially depend on working with experimentalists, in particular TEM or high resolution
Yes.
people, characterize the domains, their
Yes.
morphology. And
Yes. The reason why DFT studies are relevant is precisely because even with TEM, these the atomic displacements, for example, they are very, very small in perovskites. So they are of the in bismuth ferrite, maybe they are of the order of 0.05 angstrom, something like this, which is not. I mean, the resolution TEM is getting there, but not there. So basically, with TEM, you
unless
don't.
the CS corrected TM's the last.
The last and fantastic, I guess, development. Maybe this will be.
Okay, we are pretty tight schedule, so thank you very much. A very interesting presentation, and we will move on to our next phase.